Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are studying Chapter 5, Thermodynamic Processes and Cycles, and we're looking at the basic Rankine cycle still. What we'll be doing in this lesson is considering how reality differs from the ideal reversible and how we can use that ideal reversible result to predict what's going to happen in reality. So how does reality differ from the idealization that we've been looking at? First of all, we're saying that everything is isobaric, constant pressure, and the reality is there are frictional losses that will result in small pressure drops across the boiler and the condenser. As far as this thermodynamic analysis goes, including those makes almost no difference, and it will have very little additional work required in the pump, but in fact, you will have some pressure drop across the boiler and across the condenser. Additionally, we're saying that the boiler is going to be so well insulated that all of the heat we put into it goes into heating the fluid and not into loss to the surroundings. Probably that's an overstatement. We're going to neglect that, but that is something that should be considered. Now the pump and turbine, the difference between their ideal reversible state and what really happens is going to be based on those process efficiencies that we looked at in the last chapter. Now remember that the efficiency is defined so that you always get a result less than 1. It's the relationship between the ideal and the actual. Now, because a pump is going to require more work input than what the ideal would predict, the efficiency for a pump is the isentropic work divided by the actual work. The work for the isentropic pump, we've said we can calculate by using V delta P, or negative delta P, and that is H2 ideal minus H1. So that ideal exit state that's isentropic across the the pump, and those should be 3s and 4s. I just realized I'm working the pump problem here. 3 and 4. Those, therefore, are still going to be exactly what we've calculated. For the actual pump, however, it's going to be the inlet conditions will be the same, but the exit conditions will change to the real exit state. We will use the pump efficiency to relate the ideal isentropic shaft work to the actual shaft work for the pump. For a turbine, the relationship is just the opposite. They will not produce as much power as the ideal predicts. So therefore, it's ratios of the delta H, but for the actual, it's going to be delta H actual. For the ideal, it's going to be delta H for the isentropic process. Let's now repeat the problem that we looked at in the last video. So we've got the ideal state, all the state properties are here, but now then we have a pump that's 72% efficient and a turbine that's 89% efficient. And we want to re-examine this problem under those conditions. Now, I've added 2 lines to our data table, okay? I want to know the difference between the ideal and the actual state. The reality is that I'm going to have the entropy change, okay? But the pressure should be what I predicted. So I do know the pressures, and I'm going to be able to back out the enthalpy using the definition of process efficiency. Let's first look at the turbine. For a turbine, the efficiency is the delta H for the actual divided by delta H for the ideal. I know that the value of the efficiency is 0.89. I know delta H for the ideal, and I know the inlet enthalpy for the actual, same as the ideal. And so therefore I can use this equation to solve for H2 actual, which is 2487.8 kilojoules per kilogram. I'm going to do the same thing for the pump, but remember that the relationship for efficiency is ideal over actual. So 0.72 is 3, the work of the pump, ideally, over H4A minus 167.5. Therefore, H4 actual is 171.7 kilojoules per kilogram. Now this is still going to be a compressed liquid, right? None of that has changed. I don't have the additional information, but I have solved for the enthalpies, and that allows me to continue the analysis. Therefore, if we wanted to calculate the work for the pump, of the actual pump, it's going to be 4.2 kilojoules per kilogram. The work of the turbine is negative 1,195 kilojoules per kilogram. The net work, therefore, is negative 1190.8 kilojoules per kilogram. Q for the boiler is 3512.1 kilojoules per kilogram. The thermal efficiency of this cycle is 1190.8 over 3512.1, which is 0.339. And the second law efficiency is 0.339 over 0.6415. Second law efficiency is only 52.85% efficient, okay? We are doing a very poor job of using our resources with this design. However, it is safe for our actual equipment, okay? If you look at state 2A, the enthalpy has increased over the ideal, which means that the quality is going to increase. We could calculate it if we wanted to. So we are actually doing a better job of protecting the exit of our turbine. The reality is we want the actual to be like more than 92%, even 95% quality at the exit of the turbine. But anyway, this is in the minimally safe region for that. But we're still not doing a good job of taking care of our environment and using our resources. In the next lessons, we're going to be looking at ways that we can modify the basic Rankine cycle to improve the performance. Thank you very much for your time.